Hello, community. Hello, community. Great that you are back. And you might ask, hey, are you sure? Topological AI systems? Are we ready for that? Yes, we are. So let's start. And if you are a subscriber of this channel, you know that in my last video, where we looked at the explicit reasoning process, and QWQ32B is a beautiful system because it really prints out each and every single sort of the machine. We had a look here at the chain of sort and we discovered something. Sometimes we already saw indication of a tree of sort and yes, even a graph of sort. So this is kind of implemented in the latest reasoning models. And you might say, graph of sort? Do you have a video about this? Yes, of course. It's more than a year ago that I showed you here the AI reasoning for how you can build a graph of sort and that it is better here than a chain of sort. So let's improve now the performance of our reasoning models. And we go here from a linear chain of sort here to a much more complex graph of sort structure in our test time compute scaling. Our O1, O3, R1, S1, L1 reasoning models. So let's say that different reasoning problems, like I've shown you in my testing, they have distinct optimal reasoning topologies. And those topologies yield higher accuracy if you apply the right topology for the right task. So easiest way is, we have the chain of sort, the tree of sort, and the graph of sort that we discovered here in the answer structure here in the reasoning process of QWQ32B. So instead of relying on simple linear chain of sort, from the very old models O1 or O3, let's have a look at the latest reasoning models. And in this video, I told you here by Princeton University, if we go beyond chain of sort, it was called reasoning flux, and Princeton University showed us how their model can outperform O1 by having some particular reasoning complexities that I can define as a user in the system then will follow in the reasoning structure. So I could predefine here my reasoning complexities, let's say for theoretical physics or for mathematics or for chemistry or for finance or for medical, whatever you prefer. But it is your reasoning structure that you want to be implemented. You just don't say, hey, just somewhere in the internet there was some idea to solve this problem. No, Princeton showed us how to do this here with our predefined reasoning complexities. So, having warmed up, let's go now for this. And we have 5 cities and we have here traveling salesman. And those are the distances I've indicated here. Whatever you like, miles, kilometers, doesn't matter. It's an NP-hard problem, combinatorial optimization, theoretical computer science, operational research. And now we do this in AI. So let's have a look. If we have a test time compute scaling, what is the result in chain of sort? What is the result in tree of sort? And hey, graph of sort? Is it really the best one? Yes, of course. So chain of sort is easy. Now we have A. You start at the city A. You go to the city B, the city C, D, E, and you have to go back to your hometown A. If you go in a linear chain, you see that we have here 10 kilometers, and maybe here 15 kilometers, and here 12 kilometers. And you might wonder, hey, is this the optimal solution? And of course, it is not. So let's go here to the next one, where we branch out in different trees. It's a tree of sort. And let's go here with an inverse time. So we start here at A, we go here at E, then at city D, C, B, and back to A. And beautiful. So this is here a different branch that we've chosen here. But the beauty is, of course, if we go to a graph of sort, because now we go from A to C, this is just an 8. Then we go from C to E, this is just a 6. And then we go from E to D, and this is just an 8. And from D to B, this is just a 7. And from B to 8, okay, we have 110. So if you calculate this, you see that a chain of sort and just the inverse time, the inverse symmetry, is also the same result. But a graph of sort gives us 39 kilometers. So this is the fastest route for our traveling salesman. So we found a winner. Now we can apply this mathematical insight now to the reasoning complexity of the next AI system. Because we say, hey, why go with a chain of sort? Why go with a tree of sort? Let's build here the interrelated complexity and find faster solution. less inference time compute. Now, this, if we do all of this here in test time scaling compute, this would be quite heavy, no? So is there any other way to optimize this system? I'm so glad that you asked, because yes, of course there is. We need some parameters, no? So at first we have here simply the calculated distance. Now we call this the topological label. This is now a mathematical numerical result, so this is really some solid result. And then we have some binary hard label, and this is simply for the later process of selecting here the best data. The binary label is 1 if we came back here, if we solve this task, and the binary label is 0 if somewhere we were lost and we could not come back to A. So we have now, please remember, topological label and a binary hard label. That's it. Now, I know that some of you might say, hey, wait, in this middle, this tree of sort, is it not enough if we go from a linear sequence chain of sort to a tree of sort with branching out in different trees? Isn't this enough? Why do we have to go with a graph system? And you're right, there are topics and there are tasks. This is perfect. So imagine you're trapped in a medicine with 3 separate rooms. In each room, there's a puzzle whose solution yields 1 digit, and your overall escape code is obtained by concatenating now the results from each single room in a logical order. Now, the beauty is now these puzzles are now independent and naturally decompose into separable subproblems. You know, we decompose a more complex problem into multiple lower complexity problems. So let's have an example. Room 1, compute the sum of the first 5 prime numbers, calculate factorial of 3, and count the number of letters in the word escape. Now you know the result. We don't have to look at this. And now it is beautiful. So we have a complex problem. We're branching out in parallel workers, if you want, or parallel, I don't know, O1 for O1 systems, since the complex main problem can be now subdivided in independent subproblems where there's no input from any other of those steps. So beautiful. So TOT can be the optimal choice for structured hierarchical problems where you have independent subproblems. Then this would be the perfect solution because you have no intercorrelated mixture of anything. You know this is a linear parallel problem and I can solve it with this topology. But now, of course, we need a little bit of spark of genius today, yeah? So we teach now an LLM to choose the best topological reasoning configuration. And yes, there's more. I just start with 3 because 3 is easy, simple. And we have a beautiful new research by Carnegie Mellon University that is building up this, and they provided here this idea for this video today for a particular complex task. Of course, if we teach an LLM, we need some training data. So let's have a look what Carnegie Mellon University came up with. So training data. We need training data. We have some reasoning data somewhere. Yeah, beautifully. And then we have a supervised fine-tuning of a base language model. And now the task is a little bit different because now we train this LLM to generate here an optimal reasoning topology policy. So the reasoning we choose, chain of sort, tree of sort, or graph of sort, this reasoning topology is now different given different tasks. So, you know, in reinforcement learning, we have a policy model and we have a reward model. And yes, you guessed it. So CMU came back and says, you know, for enhanced reasoning, we do now a topological scaling. And he would say, hey, finally, some new marketing terms. Isn't this beautiful? And here another marketing term. And we start by a topological tuning. So Carnegie Mellon tells us, hey, we perform here the classical supervised fine-tuning using a high-quality topological reasoning data set. Selected now by, careful, another marketing slogan, tag. And we split here the training data into the training data set and the test data set and evaluation data set and whatever you like. And the training data is selected through a simple 3-step process. We make sure we have some diversity sampling, we have the correct answer filtering, and we have some rejection sampling that we know from the classical SFT. And then we have the data. Then we have our training data set, and then we train the model using here the next token prediction on this curated TAG data set. And Carnegie Mellon, I don't know why, that they decided to go here for a QN2 Vision Language 7B Instruct. Maybe not the best model, maybe not the most up-to-date model, but hey, CMU decided this is it. if you want to know more, because data, the quality of the data is so important. So let's have a look at TAG. TAG stands for another marketing slogan, topological annotation generation. And yes, they were talking about RAG. And then they thought, hey, can we find something similar? Topological annotation generation sounds great. So what is it? We ask an LLM to prompt here large synthetic data sets. And you might say, hey, congratulations, what a great idea. And this LLM solves now here different reasoning topologies. So it provides now a synthetic data set for CoT, ToT, and GoT. Great. Please be careful about the LLM, because this should really be able to generate a complex multidimensional reasoning path in a nonlinear submanifold for a graph of sort. And then I just showed you the topo level and the hard level. I showed you here for the traveling salesman problem how you can calculate here the topo level, and the hard level is a binary indicator, 1 for correct, 0 for incorrect, and you say, simple, easy, piece of cake. So, check. We understood topological tuning. We are training, scaling here. So this is here at the training time. This is not a test time scaling, a training scaling approach that fine-tunes here a base LLM and to learn how to generate optimal reasoning topology policy. Because, you know, the policy LLM defines here the action that it will take. And give you here the result by Carnegie Mellon University. This leads here to a 5% accuracy improvement over non-topological tuned models. And then CMU had another idea. They said, you know, if we have a topological tuning, let's do a topological reward system. And you might say, yes, 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 this is it. So we have now an, careful, inference scaling model method. So a test time compute scaling method, leveraging here a multitask topological reward model. Surprise, surprise, it will be the same like the one before, to dynamically select the best reasoning topology and the winning answer at the test time. So inference time compute. You remember the difference between the two models is just a different head. More about this in a second. And then CMU tells us, you know what? If we go crazy, we combine both of A and B, and we have now a hybrid scaling. So we do have now a new training scaling, so a training time scaling, and an inference, a test time scaling methodology to maximize the performance here of our new reasoning models that apply now the correct reasoning topology for a specific task in test time compute scaling. And they tell us here, if we go with this little QN2, we achieve the highest improvement. This is plus 10%. Well, 10%, take it or leave it, we take it. And then marketing, yeah, CMU, they are amazing here in marketing. We have now a new framework, and we call it now, CMU calls it a topological scaling framework. TSF. And they say, hey, we introduce here a topological scaling framework which operates here a competitive selection process where the optimal reasoning structure and the best answer for each problem here are dynamically determined at test time. So we do have a test time compute scaling, inference time compute. So the TSF works at TTS. Now you know exactly what it means. And if you want, here in the classical term, a hierarchical pipeline that integrates here the post-training here from the training time with an inference time rewarding system. And this, careful, new marketing term, enables now an adaptive topology selection process. And you are absolutely amazed by these marketing geniuses, and I have to tell you, yes, but did you notice something? We are not here in reinforcement learning. We're here just in two separated processes here. In the training time optimization, and then we have a test time reward. So careful, the reward system is now not doing reinforcement learning, but is an independent model that is now a pure reward model in the test time compute. Careful. Just to make this clear. Remember test time compute scaling, we had our CoT, ToT, and GoT. And I told you, hey, this is quite heavy if you do this here really at inference time test time compute scaling. So it's a good idea to prepare in the training time compute, no, like in the good old models here, the non-reasoning models. Yeah. So what they did here, both their models, and you know, we are talking here about the policy model that generates here the candidate response and defines the action to be taken, and the reward model. This is not a topological reward model, so we have TRM. and this evaluates and scores now these candidates that were generated by the policy model based on a specific range of quality metrics that it has been fine-tuned on. Great. But you remember, those models have the same backbone, but they have a different objective here, and they have different output layers. Talking about objectives, just to make it clear, the reward model is not used to then optimize the policy model like in a reinforcement learning, but the reward model is then transferred here to our TTS scaling here in inference time, and it provides here the selection of the optimal response without a separate reinforcement learning training phase. So careful, they invented here something different. What is the core idea? Well, that's easy. The topological reward model. Now, this is now something interesting, and you might say, why do we need this? So let's have a closer look. It learns to predict here an aggregated, and this is the solution, aggregated reward score by minimizing here a particular loss function, beautiful, such a regression or a ranking loss against the targets. So this process here is essentially a form of supervised learning, where the model is provided with explicit examples, see our tag, of what constitutes here a good response. So these explicit examples, you remember, they have here the continuous confidence score. These are our calculated travel salesman distances that the salesman travel between the 5 cities. This is the topo labels, 44 or 39 in our example. And then we have a binary correctness judgment, the hard labels. So this is 1 for success and 0 if you fail. So we have those examples, beautiful, and TRM has now a loss function. Now, why would we need now an AI system for this? Because we do have 2 parameters. No? We have a success parameter, and then we have a parameter that simply in the travel salesman counts the kilometers traveled. There are more factors to this. And they say we need an additional reward model now, a topological reward model, that is now fine-tuned using here the supervised learning and everything. And we have this now as a secondary, if you want, reward system that now integrates multiple factors. The correctness of the answer, this is 0, 1, but also the clarity of the response. Was the answer generated here in a concise way, in a clear way, in a structured way, in a logical way, in a whatever you like? So you see we are here more on the soft factors. So here we depend heavily on the training data, but they try to bring in all these additional factors into our topological reward model. Okay. So it learns here to map here the raw signals, like the topo label and the binary hard label, into a much more integrated reward score, taking into account also the soft factors if you want. So this is now depending here on the quality of your LLM that you use to get, for example, a right score for the clarity of the response, or was it really concisely deducted? Was it logically perfect? So you see, this could be a little bit difficult. Just to make this clear again, typically we have a reward model that be used to further fine-tune the policy model via reinforcement learning, but in this particular framework, CMU decided no. We use the TRM just applied as a selection mechanism that we activate in the inference computation in test time compute scaling. Careful. And the training of the TRM is a supervised fine-tuning on a high-quality data set that's also used here for the other one. So it doesn't have to explore here the complete exploration space or the solution space via a reinforcement learning methodology. And they argue we did this topological reward modeling, to simplify the process, the computational process, because this allows here for a single pass selection among candidates, because we have here a trained LLM that is now giving us here all the integrated quality sources for the reward feedback. For if you're not that familiar, you know the policy model outputs text tokens. Its training loss, it's using a particular loss function, is based on how well it predicts the next token in a linear sequence. Now, normally the reward model outputs here a scalar, a reward value, or a ranking score, whatever you like to call it, and is typically trained using here a regression or a ranking loss function. And this is really different here from the cross-entropy loss that we use here normally for the prediction of the next language token in a linear sequence. But, of course, yeah, they have different heads. This is all topological reasoning. Topological reasoning sounds a little bit strange, but it is rather easy to understand. Normally, the O1 or O3, no, you have predefined reasoning topologies. Long chain of thought in the reasoning models. By now we say, hey, you know what? Let the system decide which reasoning topology to choose given, in the inference time here, my particular task. So I want that the system chooses itself the optimal reasoning structure that might vary given my particular query, my particular problem, and therefore I need an AI system to dynamically learn here the optimal performance in choosing here the right reasoning topology. Okay. Now, again, remember, showed you Princeton University, we achieved exactly the same where I defined here my complex reasoning templates, if you want, multidimensional interconnected templates that we can build upon and we can combine in a modular way. It is rather similar if you think about this. Also here I had the option here to build my own reasoning structures, and here this is done here simply by a syntactic data generation via another AI system, another LLM or vision language model. Great, this is the study. This is March 6th, 2025, Carnegie Mellon University, USA, okay. It is called SOLAR, Scalable Optimization of Large-Scale Architecture for Reasoning. Really interesting. It's a little bit challenging because, yeah, they tell you, hey, we have a new topological reward model and a new topological annotation generation system and everything. But if you look at the explanation of their framework, this is it what you find. And reading this paper here, and I saw this, I thought, help, I don't get it. What is happening here? And this is the reason why I read it. I thought that I understood it. And then I built up here and I designed this video for you. Now I hope you have a better idea and you don't start here with this one, because the idea is also simple, quite interesting. This is the performance data if you want. So we have here a normal baseline model for reasoning, beautiful, and we have in accuracy and percentage 79%. And then we have the baseline, and then we have here the topological reward model. This makes a beautiful jump to 88%. And if we only go with here baseline with topological tuned, you know, just point A, we have 84. And if we combine both the syntactic scaling of the, if you want the training time and the test time compute scaling, if you combine both, we're at 89.02%. So you see, we go from 79 to 89.02. So this is exactly what they tell you. Hey, the maximum jump we perform here is 10.02 percentage point compared to a baseline model. And this was the QN2 VL7B instruct, if I remember correctly. Great. Let's come to an end. Let's understood what we just achieved. They have chosen a particular way of a multitask evaluation structure for their topological reward model. Now, this is kind of a challenge. Now, this is kind of interesting because instead of having for reinforcement learning for real important separate reward models, like you go for factual correctness, or you go for conciseness, or you go for whatever you like, putting all the factors into a general multitask TRM, a unified model, has its advantages, but also maybe its drawbacks, especially if the training data are not the best training data that were synthetically generated by a LLM that is quite old. So, okay, they argue that their multitask TRM leads to a better overall performance compared to if you use multiple single task reward models. I've never seen MTRM before, or STRM for single task topological reward models. So you see, this is full of new technical terms, of new marketing notation, but the main idea is absolutely interesting. So they integrate two key scaling strategy. At first they go for the training time scaling, and then they go for the inference time scaling. And they prepare, if you want, the model here with a simple training time scaling with a topological tuning. So they fine-tune standard LLM or a vision language model on this syntactic tag annotated training data. So we have then a model that learns to choose here the optimal reasoning policies. And at the inference time, we have then the topological reward model. So we can employ now a multi-task topological reward model, given its internal complexities, to select now the best reasoning topology, chain of thought, tree of thought, or graph of thought, or even a more complex reasoning topology. Maybe in my next video I will have some new data on this and answer this in a single inference pass. So you see, it is interesting to integrate now something that is already there. At least in QWQ, we saw that we had kind of a, if you want, topological reasoning structure. But maybe it was not done or chosen here by training here specific LLMs, either on the topological tuning here, on the fine tuning, and or on the topological reward functions. Maybe with QWQ, it was more inherent in the training data. And now Carnegie Mellon University makes it here explicit here in specific reward functions that we have here the topological reward model with a multitask aggregation of whatever are the most important facts. But of course, you have an option to this, and as I showed you by Princeton University, reason flux. Interesting to see this actual development taking place here now in this week. And yeah, this is not the end. There are some new developments coming up, so maybe you want to subscribe to this channel, and I see you in the next video.